Modern cosmology was built on a single assumption that dark energy, the force accelerating the universe, never changes. It was never fully proven, only stable enough to trust. That assumption shaped everything we believed about the future: endless expansion, fading into a cold and silent big freeze. But now, a new signal demands a second look. The Dark Energy Spectroscopic Instrument, DESI, has returned data our standard models struggle to explain. It suggests the invisible engine driving cosmic expansion may be changing. If the parameter shaping the universe can move, then the ending we planned for can move as well. And the question is no longer how the universe ends, but whether we ever understood what was pushing it apart. To understand the gravity of this new signal, we must first look at the case file we believed was closed. For nearly 30 years, the scientific community has operated under a unified consensus regarding the fate of the cosmos. The verdict was unanimous: the universe would end not with a bang, but with a whimper. We called it the Big Freeze. The logic was elegant in its simplicity. If dark energy is a constant force pushing galaxies apart, and it is stronger than gravity, then expansion will continue forever. Over trillions of years, galaxies will drift beyond our observable horizon. Stars will burn through their fuel and fade into iron ash. Black holes will slowly evaporate into Hawking radiation. The final state of reality would be an infinite expanse of cold, dark, and empty space, hovering just above absolute zero. For a generation of physicists, this grim ending became the standard model. It was comfortable because it was mathematically stable. But looking back, we must admit a difficult truth: we didn't prove this ending was inevitable. We only proved that our instruments at the time were consistent with it. And comfort, unfortunately, is often the enemy of inquiry. That comfort evaporated with the latest data release from the Dark Energy Spectroscopic Instrument, or DESI. Perched high in the Arizona mountains, this instrument was designed to map the expansion history of the universe with unprecedented precision, effectively auditing the cosmic books. What DESI found was an anomaly, not a conclusion, but a deviation from what our models expected to see. When combined with other major data sets, the constant force we relied on to predict the Big Freeze appears to be wavering. The data hints that dark energy's grip on the universe may be weakening over time. This is not supposed to happen in the standard model. If this signal is real, it means the engine of cosmic expansion is running out of steam. The glass wall of our Big Freeze theory hasn't just been scratched, it has developed a structural crack. But to understand why this crack implies a catastrophe rather than just a correction, we first have to understand the wall it just broke. To understand why the new DESI results are so unsettling, we have to go back to the moment the current paradigm was established. Let's travel back to 1998. At that time, the expansion of the universe was already a known fact, established by Edwin Hubble nearly 70 years prior. But the detectives of that era, cosmologists, were trying to answer a specific question: how fast is the universe slowing down? At the time, the logical expectation was that expansion should be decelerating. Gravity is an attractive force. The mutual pull of all the galaxy's stars and dark matter in the cosmos should be acting like a brake on the expansion initiated by the Big Bang. Two independent teams of astronomers set out to measure this deceleration using type Ia supernovae. These stellar explosions are the universe's standard candles. Because they explode with a consistent peak brightness, they allow us to measure cosmic distances with remarkable accuracy. By comparing how bright they look to how bright they actually are, and then measuring how much their light has been stretched by the expansion of space, a process known as redshift, we can reconstruct the expansion history. The astronomers expected to find that distant supernovae were brighter than a constant expansion would predict, proving gravity was winning. Instead, they found the opposite. The supernovae were fainter than expected. They were much farther away than the math allowed. The universe wasn't slowing down, it was speeding up. This was a seismic shock. Gravity wasn't the only player on the board. Something else was pushing back, overpowering gravity on the largest scales. To explain this, physicists dusted off an old idea Albert Einstein had once discarded as his biggest blunder: the cosmological constant, denoted by the Greek letter lambda. In this new model, dark energy was interpreted as a property of space itself. Think of it as a flat tax on the universe. For every cubic meter of empty space that comes into existence, there is a fixed cost, a constant amount of repulsive energy. As the universe expands, it creates more space. More space means more repulsive energy. More energy leads to faster expansion. It was a perfect self-reinforcing loop, and most importantly, lambda was constant. It didn't change over time. It was the perfect mathematical alibi for a universe that refused to slow down. Lambda didn't win because we saw it directly. It won because everything else fit the data worse until we started measuring with less mercy. The discovery of acceleration earned the 2011 Nobel Prize in Physics and gave birth to the standard model of cosmology, technically known as the Lambda-CDM model. The name itself is a recipe for our universe. Lambda represents dark energy, about 68% of the energy budget. CDM stands for cold, dark matter, about 27%, the invisible scaffolding that holds galaxies together. The visible matter stars, planets, us makes up a humble 5%. For 2 decades, this model has been a golden cage. It is frustratingly successful. It explains the distribution of galaxies, it matches the ripples in the cosmic microwave background, it predicts the abundance of light elements. Because lambda assumed dark energy had a constant density, it predicted the big freeze with near absolute certainty. The math was robust, the predictions were verifiable, and the anomalies were buried within the margins of error. We became comfortable. We started to confuse the map with the territory. We assumed that because lambda fit the data best, it was the truth. We stopped asking if dark energy was a dynamic living force and accepted it as a static background condition. We allowed ourselves to believe the mystery was solved, but scientific certainty is often just a systematic fog, a blindness induced by the limitations of our tools. We were looking at the universe through a keyhole, and through that narrow view, everything looked constant. To challenge a model this successful, you don't need a new opinion. You don't need a debate. You need a new instrument. To challenge a consensus as solidified as the Big Freeze astronomers couldn't just rely on more observations. They needed a fundamentally better way to see. They turned to the Nicholas U. Mayall telescope at Kitt Peak National Observatory in Arizona. Inside its massive dome sits the machine built to dismantle our assumptions, the Dark Energy Spectroscopic Instrument, or DESI. If the universe is a system under investigation, DESI is the instrument built to measure it without rest. Previous surveys looked at the sky like a wide-angle camera, taking pictures of everything at once. DESI operates differently. It is a coordinated system of mechanical precision. At its heart lies a focal plane packed with 5,000 robotic positioners. These aren't massive industrial arms, they are delicate, high-speed actuators, each carrying a fiber optic cable no thicker than a human hair. Every 20 minutes in a synchronized mechanical ballet, all 5,000 robots reorient themselves with 10-micron accuracy, that is a fraction of the width of a sheet of paper. They lock onto 5,000 specific galaxies or quasars, simultaneously capturing their light before the Earth's rotation moves them out of view. This isn't just photography, it is spectroscopy. By splitting the light from each galaxy into a rainbow of colors, DESI measures how much that light has been stretched by the expansion of space, its redshift. Because light takes time to travel, looking deeper into space means looking further back in time. DESI is effectively slicing the universe into 11 billion years of tomographic layers, creating the largest 3D map of the cosmos ever assembled. The goal of this engineering marvel is to filter out the systematic fog. By collecting data on tens of millions of galaxies, DESI suppresses the random noise that plagued earlier studies. It provides a clean, high-fidelity signal of how the universe has expanded over its history. First, we make sure the noise can't fake a universe. Then, to measure the expansion rate within that map, we bring in a ruler older than the galaxies themselves. In our everyday life, if we want to measure how fast a car is moving away, we need to know how big the car actually is. In the vastness of the cosmos, we need a standard ruler, an object of known size that we can track across billions of years. DESI uses a ruler imprinted in the early universe baryon acoustic oscillations, often called BAO. 380,000 years after the Big Bang, the universe was a hot, dense soup of plasma. It was not silent. Quantum fluctuations created sound waves, ripples of pressure traveling through the fluid of light and matter. These were literal sound waves expanding outward from overdense regions, like ripples in a pond. But as the universe expanded and cooled, a critical moment arrived. The plasma neutralized. Light broke free, becoming the cosmic microwave background, and the pressure driving the sound waves vanished. The ripples effectively froze in place. These frozen ripples left a permanent scar on the distribution of matter. They created slightly denser shells of material where galaxies were more likely to form. Today, 13 billion years later, we can still see this pattern. If you look at the statistical distribution of galaxies, you find a subtle preference for them to be separated by a specific distance. That distance is our standard ruler. It measures exactly 150 megaparsecs, roughly 490 million light years. Because we know the exact length of this ruler from the physics of the early universe, we can hold it up against the sky at different epochs. By observing how big this 150 MPC ruler appears to be at different redshifts, we can calculate exactly how fast the universe was expanding at that specific moment in history. The physics is solid, the ruler holds, the map holds. And yet, when DESI projected this data onto the screen, the dashboard needle refused to stay where it should. This is where the tension breaks into the open. To quantify dark energy, physicists use a value called the equation of state parameter, known as W. In the standard Lambda-CDM model, the one that predicts the big freeze. Dark energy is the energy of empty space. Its density never changes. Therefore, W must be exactly 1. It should be a flat line stretching from the past into the future. A value of 1 means the push of dark energy is constant, leading to eternal exponential expansion. But when the DESI team combined their 3D map with data from the cosmic microwave background and type Ia supernovae, the best fit line didn't stay flat. It drifted. The telemetry suggests that W is not 1. Instead, the data prefers a solution where W varies over time with WA0. Specifically, the trend indicates that in the recent cosmic past, the value has drifted upward, becoming less negative, closer to 0. In plain English, the data suggests dark energy may be losing strength over time. The statistical significance of this drift is approximately 4.2 sigma. In the strict court of particle physics, 5 sigma, a 1 in 3.5 million chance of being a fluke, is required to claim a discovery. However, 4.2 sigma implies a confidence level of roughly 99.9997%. It is a signal strong enough that it cannot be dismissed as random noise. It is a glitch in the standard model that refuses to go away. The dashboard is flashing. The engine of expansion, once assumed to be constant, no longer appears stable. 4.2 sigma isn't the verdict, only the moment the room goes silent. Physics doesn't do certainty, it does thresholds. We are currently standing on a threshold that demands we look into the abyss. If W stays at 1, we freeze. But if the parameter continues its current trajectory, drifting upward and crossing the critical line, the rules of the game change entirely. The big freeze relies on dark energy winning the tug-of-war against gravity forever. But if dark energy weakens enough gravity, the patient, relentless architect of the universe will eventually regain the upper hand. If the parameter can move, then the ending can move. And the math suggests that some endings are moving toward us. If the DESI data is correct, and the dark energy parameter W continues to drift upward, crossing the critical threshold of 1 and heading toward 0, then the fundamental geometry of our future changes. The big freeze relies on a specific condition that the walls of the universe expand faster than gravity can pull them back. But if the engine of expansion falters gravity, which has been patiently losing the tug-of-war for 13.8 billion years, will seize the advantage. This scenario leads to the big crunch. But to call it a crunch suggests a sudden, violent impact like a car crash. The reality is far more insidious. It is a slow, agonizing suffocation caused by the laws of thermodynamics. Imagine the universe as a cylinder in an engine, and space-time is the gas inside. For billions of years, the piston has been pulling out, expanding the volume, cooling the gas, and allowing life to flourish in the low-energy vacuum. But in a collapsing universe, the piston stops. It reverses direction. The horror of the Big Crunch is not primarily about objects colliding. Collisions are rare in space. The horror is about density. As the cosmos begins to contract, the observable universe shrinks. The galaxies don't just get closer, the space between them disappears. This creates a thermodynamic trap. Currently, our universe acts as a massive heat sink. Stars generate heat and they radiate it out into the cold, endless void. Life relies on this gradient. We take in energy and dump waste heat into the cold sky. But in a contracting universe, the void stops being cold. As the scale factor of the universe decreases, the energy density of radiation rises furiously. Photons that were once stretched out and harmless are compressed back into high-energy states. The universe becomes a closed system with contracting walls. There is no outside to vent the heat. The temperature of the entire cosmos begins to rise. We are not moving toward a cold, lonely death, but toward a state of blinding, white-hot integration where the concept of individual existence becomes thermodynamically impossible. When the global expansion reverses, the local consequences are not just mathematical, they are visceral. What would this look like to an observer, perhaps a descendant of humanity watching from a safe orbit around a stable star? The process would likely play out over billions of years, unfolding in a terrifying sensory timeline of 3 distinct phases. Phase 1. The silence of the redshift. For eons, astronomers have relied on redshift, the stretching of light toward the red end of the spectrum, to measure the recession of distant galaxies. It is the signature of expansion. But as gravity applies the brakes, the redshift slows. Eventually, there comes a turnaround point. To the observer, the distant universe would seem to freeze in its trajectory. The cosmic horizon, which has been hiding galaxies from us for billions of years, would stop receding. The sky wouldn't look different yet, but the data would show a terrifying flat line. The expansion has stalled. The expansion has stalled. Phase 2, the onset of blue shift. Then the motion reverses. Gravity begins to reel the cosmos back in. Light waves traveling through space are no longer stretched. They are compressed. Their wavelengths shorten, shifting toward the blue, then the violet. Galaxies that were once fading dots begin to brighten and rush toward us. The Andromeda Galaxy and the Milky Way will have long since merged, but now clusters of galaxies, millions of light years away, are encroaching on our local space. The sky becomes crowded. The darkness between the stars begins to fill with the light of 1 trillion approaching neighbors. Phase 3. The thermal inversion. This is the final and most terrifying phase. The most abundant photons in the universe are not from stars, but from the cosmic microwave background, or CMB, the leftover heat from the Big Bang. Right now, this radiation is a chilly 2.7 Kelvin, invisible to the naked eye. But as the universe shrinks by a factor of $1,000, that background radiation is compressed. Its wavelength shifts from microwave to infrared. The temperature of space rises to 300 Kelvin room temperature. At this point, the night sky is no longer cold. It is warm, like the air on a summer night. Planetary atmospheres begin to boil off, not from their own suns, but from the heat of empty space. As the contraction continues, the background shifts into the visible spectrum. The sky turns a dull red, then a bright orange. The CMB rises to 3,000 Kelvin, the temperature of a red dwarf star. At this moment, the concept of night ceases to exist. The sky is now a solid wall of fire, as bright as the surface of a star in every direction, 24 hours a day. Shadows vanish. Stars cannot cool themselves. They are bathed in radiation hotter than their own surfaces. They are cooked from the outside in. Matter is crushed into plasma. Atoms are stripped of their electrons. The complexity of chemistry, biology, and geology is unraveled. Finally, everything, every star, every black hole, every memory of history is compressed into a single point of infinite density. This is the inversion. The timeline of the universe runs backward, returning to the primal fire from which it was born. It is a terrifying prospect, but in the strange logic of cosmology, this violent end might be the only reason we exist at all. Some theories, like Roger Penrose's conformal cyclic cosmology, suggest that this big crunch is not a death, but a reset. The compression may erase certain structures, potentially creating the conditions for a new cosmological cycle. If the DESI data is right, we are not living in a dying universe. We are living in a breathing one that is currently inhaling, preparing for the long, slow exhalation that will ignite the next aeon. So, which is it? Is the universe a machine running out of fuel, destined for a fiery collapse? Or was the DESI signal just a statistical phantom, a systematic fog that will evaporate when we clean the lens? The honest answer, and the most scientifically exciting one, is that we don't know yet. 4.2 sigma is a warning, but it is not a verdict. In the history of physics, signals this strong have vanished before. It is possible that our understanding of type Ia supernovae is slightly flawed, or that there is a subtle calibration error in the way we combine datasets. That is why the next decade is set to be the golden era of precision cosmology. DESI has only released its first batch of data. There are years of observations still being processed, but DESI will not be testifying alone. A new generation of witnesses is taking the stand. ESA's Euclid mission is already in orbit, mapping the geometry of the dark universe with a different set of instruments. NASA's Nancy Grace Roman Space Telescope will soon join it, providing a panoramic field of view 100 times larger than Hubble's. And on the ground, the Vera C. Rubin Observatory is preparing to switch on. It will not just take pictures, it will record a 10-year movie of the southern sky, cataloging billions of galaxies and millions of supernovae. We need these different witnesses because different probes fail differently. If DESI, Euclid, and Rubin all point to the same drifting needle, if they all agree that W is climbing away from 1, then the case is closed. The standard model will fall. It is humbling to realize that the difference between an eternity of cold isolation and a violent, fiery rebirth comes down to a number. The fate of 2 trillion galaxies, the legacy of every star that has ever shined, and the ultimate conclusion of time itself all hinge on the next decimal point of the dark energy parameter. We humans have a bias toward narrative. We want the story of the universe to have a structure, a beginning, a middle, and a safe, predictable end. But physics does not care about our comfort. It does not care about our desire for permanence. It cares only about the conservation of energy and the curvature of space-time. For 30 years, we thought we were living in a universe of infinite drift. Today, the data suggests we might be living in a universe of cycles, a breath in, a breath out. The ending is no longer written in stone. It is being written right now in the light of distant stars falling onto fiber optic sensors. And for the first time in history, we are close to turning the next page.